Example 4.3.1. The setup for this problem says you would like to start a scholarship at your alma mater. You expect to earn 8% per year on your investments. How much must you deposit today so that the scholarship can pay $10,000 per year in perpetuity, with the first payment occurring 1 year after your gift is received? Okay, we've got a problem we need to evaluate that involves cash flows spread out over time. This is a time value of money problem, so we're going to use our three-step process to work this one, where the three steps are: step 1, draw the timeline, label all the information we're given. Step 2, use that timeline to identify the type of cash flow we're looking at, so that then in step 3, we know which tools we can use to solve for the missing variable in the particular problem. All right, so let's start out by mapping our cash flows for this problem. All right, so for this one, today at time period 0, we are looking for how much must we deposit today. So we don't know what the cash flow at time period 0 is going to be. So I'm just going to put a question mark there for now. I do know that whatever deposit I put in, I expect to earn 8% interest, and then I want to be able to use that interest accumulation to pay out $10,000 1 year from today. All right, it says how much must you deposit today so that the scholarship can pay $10,000 per year in perpetuity, with the first payment occurring 1 year after your gift is received. So I'm going to deposit something today. It's going to accumulate interest for 1 year. I'm going to pay out $10,000 from that amount. And then 2 years from today, it's going to pay out another $10,000, right? It says in perpetuity, we want to pay out $10,000 per year. Perpetuity is just a funny word for forever. It just keeps on happening over and over again. So 1 year from today, $10,000 cash outflow from the account, or cash inflow to the student that's receiving the scholarship. A year after that, or 2 years after the deposit, another $10,000 cash flow to the scholarship recipient. And then that pattern is just going to go on forever. Right? Every year, we're just going to take the accumulated interest and pay it out. And for the scholarship, we're going to leave the original deposit, the original principal, in the account, let it earn interest for another year, and then scrape off the interest and pay it out as the scholarship, and just let that pattern go on forever. As long as we leave the principal untouched and it continues to earn 8% interest, then there's no reason that that pattern would ever need to stop. Okay, so that's step 1. We've mapped out all the available information. And step 2 is to identify the type of cash flow we're looking at. Well, in this one, there's a giant hint. It says perpetuity right in the question, so we know we're probably looking at a perpetuity. But just to be sure, let's look at our different types of cash flows. We know it's not a lump sum because it's happening over and over again. Okay, perpetuities. Here, a perpetuity is a series of equal cash flows paid at regular intervals that last forever. And if we look at the example timeline for a perpetuity, we have something that looks awful familiar, or awful similar to this particular example. It's even the same cash flow of $10,000 at regular intervals that goes on forever. So sure enough, we are looking at a perpetuity. It is not a growing perpetuity, because a growing perpetuity would have cash flows either growing at a set rate or shrinking at a set rate forever, but there would be a set growth rate in between the cash flows. And that's not what we have with this example. We've got the same cash flow over and over again. So it's just a perpetuity. All right, so let's go ahead and label that. We know we're looking at a perpetuity. And the reason that it's important for us to be able to figure out what type of cash flow we're looking at is, 1, we know what tools are available to us to evaluate this thing. If we're looking at perpetuities, we really just have one tool available to us, and that is the present value of a growing perpetuity, or the present value of a perpetuity formula. You could make an argument that you could use a spreadsheet as well. It would just do the arithmetic for you, but there's not a present value function in any spreadsheet that I'm aware of that will allow you to deal with a perpetuity. You would just be doing the math in the spreadsheet. You wouldn't be using a particular function. So that's why I've only listed the formula solution here. Now there's another quirk on this cheat sheet, and that is I have only listed the present value of a growing perpetuity formula. That is equation 4.04 for evaluating both perpetuities and growing perpetuities. And there's a reason for that. If we look at the formula sheet that goes with the text, we see two formulas related to perpetuities. We have the present value of a perpetuity, which is what we're dealing with here, just a regular perpetuity, where the present value is the cash flow divided by the interest rate. And then we have the present value of a growing perpetuity, which is the cash flow divided by the quantity of the discount rate minus the growth rate in the cash flows. That G stands for the growth rate in the cash flows. All right. Well, the reason I've only listed one formula here is just to keep us from having to memorize two different formulas or bouncing back and forth or being confused about which formula we might apply. In fact, this present value of a growing perpetuity formula will work for every kind of perpetuity, whether it's just an ordinary perpetuity or it's a growing perpetuity. I shouldn't say ordinary perpetuity. It's a perpetuity with level cash flows or a growing perpetuity. And the reason they're the same is because this growth rate G, if that guy is 0, which it is on a perpetuity with level cash flows, they're not either growing at a set rate or shrinking at a set rate, then that G is 0, then it just drops out, right? It's R minus 0, which anything minus 0 is itself, and you're left with the cash flow divided by R, which is exactly the formula for the present value of a perpetuity. So that's why I've only listed the one formula on the cheat sheet. You can use both formulas if you want to bounce back and forth. That's perfectly fine. There's nothing wrong with that. Using just the one formula simplifies things, at least is the way I think about them. So that's why that one is there. So for this particular problem, since we're dealing with a perpetuity, the only tool that really makes sense to use is the present value of a perpetuity formula. All right, so the present value of a, we'll use the growing perpetuity formula just to see how it works. Now, importantly, I'm going to write PV sub 0 here because there's an important timing issue that happens with these formulas. So present value as of time period 0 is equal to the cash flow at time period t divided by R minus G, where cash flow at time t is the cash flow that happens one period after the time we're looking for the present value. So the present value sub 0 stands for 0 on our timeline, and then CFT, in fact, we'll go ahead and write CF1 in this case instead of t because we're looking at the cash flow at the end of year 1. Right, so we'll talk a little bit more about that timing difference in just a second. R is our interest rate. That's our discount rate of 8% in this case. And then G is the growth rate in cash flows. That is the rate of change from one cash flow to the next. In this particular problem, that's 0. So our present value at time period 0 is equal to the cash flow one period later. In this case, that's 10,000. Divided by the discount rate, R, which is 8%, expressed as a decimal, that is 0.08, and then minus G, that's the rate of change from one cash flow to the next. Since these cash flows are the same, that guy is 0. Right, so that is equal to 10,000 divided by 0.08. So our present value as of time period 0 is equal to 10,000 divided by 0.08 of $125,000. So if we were to deposit $125,000 today, then that $125,000 would earn 8% interest, which is going to be $10,000 over the next year. We could pull off that $10,000 and pay it out, and it would leave the $125,000 intact, and it would earn interest for another year, which would total to $10,000. We could pull off that $10,000 in interest, pay it out, which would leave the $125,000 intact. And so all we would have to do to create this $10,000 scholarship that could pay out every year is deposit $125,000 today and just let that guy earn interest and pull the interest off every year and pay it out.